Hello everyone, my name is Matchima Buddhanoy. Today I will be presenting Descrambling the Scrambler in NAND flash memory. Data scramblers are used to randomize store bit data pattern before programming. This is to ensure that all cells' threshold voltage level are evenly distributed. As you can see here on the left-hand side, threshold voltage distribution that erase state and program state are evenly distributed. This is the comparisons for the case where data scramblers is not used. Without data scrambler, non-uniform data pattern can cause unevenly threshold voltage level distribution. This will later on cause the program and read disturbance, and that will impact the reliability of NAND flash memory. So the issue is, if we know the data scrambling key, uh, that can help with the system integrator to improve data reliability and improve error management strategy. But the main issue is the scrambling keys are undocumented and it is inaccessible in commercial NAND chips. Our goal in this work is to recover the scrambling key from the unmodified commercial NAND flash memory chips to help the system integrator to achieve the goal. This is the outline of today's talk. First, I will go over the background of flash-based SSD, and then I will talk about the scrambling key extraction process. Then we will go over the experimental setup, test flow, and algorithm, and then we will show some experimental results and conclude today's talk. Before we go into the data scrambling process, let's take a look at the background of the flash-based SSD. This is the flash-based SSD that you would get from the store. The main components are controllers and then flash memory chips. Controller will essentially be a brain of the components. It will do address mapping, error corrections, and garbage collections. The NAND chips, on the other hand, it will just store the data. Sometimes controllers come with scrambler. There are also times that some NAND flash memory chips come with the on-chip scrambler. And if you can see here that when hosts wanna write the file into the NAND flash memory chips, at one point, scrambler data will go to the scrambler. And in this work, we will focus on the scrambling on the on-chip scrambler. So it's gonna be the bottom case because we have access to raw flash memory chips. Let's take a look at data scrambler and descrambling process in a little bit more detail. Let's say we want to program user data into a NAND flash memory page. The key will get derived using linear feedback shift register based on the page number, flash page number. So what will happen is data that would get programmed into NAND flash memory will be a randomized data because the data user will get XOR with the key that derived using linear feedback shift register. So useful information will become randomized. So to read the scrambled data, first data from NAND flash will be read, and again linear feedback shift register will derive the key based on the page number. And again, the randomized informations from NAND flash array will get XOR with the key, and that will give a user the valuable information. So this is how data scramble and descrambling process happen. In our scrambling key extraction process, we first program one data set into NAND flash array. In this example, we give all 55 as a first pattern that we will program into NAND flash array. So the 55 pattern that we put in will get XOR with the key based on the page number, and that will make the data that get programmed into the NAND flash will be randomized. And if you can see here in the threshold voltage distribution in NAND array, that the erase state and program state will be equally distributed 50-50. And then the next step is, without erase operation in between, we will program the inverted pattern of the previous pattern. So let's say if you do all 5 in the first step, so in the override step, the next step will be inverted of all 5, which is all AA. So what would happen is the all AA will get XORed with the same key, and that would generate the inverted randomized pattern. And if you can see here in the NAND arrays, what would happen is the erase state will move to the program state, and the program state will remain in the program state. So this is the characteristic of NAND flash memory, where erase state can move up to the program state through program operations, but the program state cannot move down during program operations. The only way that you can move program state down is through erase operations. So now all the cells are in the program stage, which is all 0. To get the key, read operation will be applied. If you can see here that without the scrambler, all cells will be in the program stage, which means it's going to be all 0. So without the scrambler, when we read out this page, it's going to be all 0. But because of the scrambling key, the all 0 will get XORed with the key. That means whatever we read out at the end, it will be the scramble key. So this is how we extract the scrambling key in the NAND flash memory chips. We first program one pattern and then override with inverted pattern of the first pattern, and then we read flash page. Let's take a look at the experimental setup, test flow, and algorithm we used in this work. This is our test setup, and this is our experimental test flow. First, we erase a flash blocks, and then we program all 5 patterns. Then we overwrite the same block with all A patterns, and then read to get the scrambling key. This is the algorithm that we used. Basically, this is more detailed version of the test flow, and the algorithm itself also include the command sequence that we use to interface with NAND flash memory chips. So our experimental evaluation will be performed on 6 different NAND flash memory technologies. We first show our experimental results on 3 NAND SLC page, and this is just a single page with a readjust the rows and columns to make it easier for everyone to understand. And if you can see here that the SLC page key reveals that there's a 16-byte sequence that repeated for 32 rows, and then the new 16-byte segment begins and then repeated for another 32 rows, and then another 16-byte segment starts for another 32 rows. So we observe this repeated behavior for a single NAND flash page, and we conclude that this is the key for the SLC page, and this is the 3D MLC NAND chip with this part number. With the same idea as the SLC single level cell storage, we apply the same idea into the multi-level cell or MLC storage. Because MLC can store 2 bits per cell, so there will be 4 different threshold voltage distribution. And if you can see here that there will be LSB page and MSB page. LSB page stand for least significant bit page, and MSB page stand for most significant bit page. To extract the LSB page key and MSB page key, we start with the LSB page key first. And again, we first program all 5 pattern. The all 5 will get XORed with the key. What will happen is cell started from L0, it will either remain in L0 or move to L2. Without touching any MSB page, override the LSB page with inverted pattern of the previous pattern, which is all AA. At this case, all the cells will move to L2. And if you can see the logic, take a look at the logic of the L2. The LSB bit will be R0. So when after the read operation, we can get the key from the LSB page. And then we move to the next step, the MSB page key descrambling. Now we will start at L2 states, and without touching anything on LSB page, we will first program MSB page with all55, and that will make cells in move to L2 or L3. And then with the inverted patterns, it will make, so the next step is programming with inverted pattern, which is again RA. So this will make the final states will be L3. So all the cells will get moved to L3. And if you can see here that the rate letter that in L3 the MSB logical bit values it's 1, which means when we read out the page value without the scrambling key, you will see all 1 patterns, which mean the key after basic read operation for that page, it's not gonna be the key because 1 XOR with the key will not be, it has to be inverted. That means the true key of the MSB page, we have to invert whatever we read out from the page. Unlike the LSB page key, because of the R0, when R0 pattern XOR with the key, it will give the true key. Next, we will show you the results from the MSB share pages. Let's start with the key for the LSB page. And again, because it is the same chip, we a single page LSB page read, we will reshape row and columns a little bit to make it easier to understand. If you can see here that the LSB page key is actually retrieved directly from the page read operation, as I mentioned earlier. And if you can see here that we see the same behavior, the same pattern, where the first 16 bytes sequence starts for 32 rows, repeated for 32 rows, and then the next 16-byte sequence starts and then repeated for another 32 rows. We see the same behavior in the MSB page. So both SLC page, LSB page key, and MSB page key show the same behavior of the 16-byte sequence repeated for 32 rows and then change. So, and again, I just want to make a note here that the MSB page key is the read out data, but inverted. So this is like a true key after inversion of the read out data for MSB page. And I just want to make a small note here that you might be observed some highlighted text in red in these two in these two tables. This is come from the bit error because of the MLC storage. The threshold voltage distributions are narrower compared to SLC. So sometimes we get some data corruption from it because of the narrow threshold voltage margin, but still that doesn't interfere with this descrambling process, because if you take a look at the overall trend, you still can see the true keys of it. For example, in the MSB page key, the first byte it's D3 and the second byte it's D4. But if you can see the second row, the third row, the repeated pattern, you still can see the overall, the correct key of the LSB page and MSB page. We further implement our technique into two different types of memory chips. The previous result was in 3D. Now we implemented in 2D, and these two results are from 34 nanometer 2D MLC NAND memory chips. And the top row is from the LSB page key, and the bottom row is from the MSB page key. And if you can see here that the behavior of the scrambling keys is different from the 3D NAND, because now you can see that 32 bytes are begins and then repeated for 16 times. Like you can see in 16 row, and in the new 32 bytes begin and then repeated for another 32 row. So different chips may have different behavior, so the scrambling key may not be the same in all of the NAND flash memory chips. And again, even in 2D NAND, we still can observe some fail bit, like the incorrected bit, because of the threshold voltage distribution get narrower. Across all of our NAND flash sample used in this work, we found out that they are unique properties of the scrambling key. First, we found out that keys are different across NAND flash pages, which mean the SLC page, LSB, and MSB share pages within a block. They all have unique key, which means even if you can retrieve a key for one page within a one flash block, the same key for that page will not be applied for other pages, the remaining pages within a block. And we believe that the physical page number determines the scrambling key through the linear feedback chip register. And the next property is keys are identical across blocks, which means if you can retrieve all the key within the blocks, the same sets of key will be applied in the other blocks within the NAND flash memory chips. And the last property is that the keys are identical across the chip of the same part number, which means if you can extract a key from only one chip, another chip that has the same part number will have the same key. So only one extractions can be applied to all devices of that model. This table summarizes all of our multi-chips evaluations. As you can see here, we evaluate our technique in different chips from 2D and 3D chips, and then storage type from SLC to MLC. As you can see here that the key length from all the chips are different, and the number of key per page, especially 2D and 3Ds, are different. And we found out that all the unique property that I discussed in the previous slides, we saw all the chips show the same uniqueness. And the last column is the number of parts that we evaluate in this paper. And we conclude that our techniques works across 6 different NAND part number, including 2D and 3D technologies, and as well as SLC and MLC storage type. In conclusion, this work we extract the scrambling key from unmodified commercial off-the-shelf NAND flash memory chips. By forcing all the cells into unknown states, we can recover the internal keys. And we found out that there's a consistent key pattern, 16 to 64 bytes periodically repeated depending on NAND technology. And the keys are page dependent, block independent, and consistent across chips. So this will give us the idea that if we can reconstruct a single block from one device, the same key will apply in another block within the same device, or in other block of the different device but the same part number. And our validation evaluations on 2D and 3D NAND chips confirm that our techniques actually widely applicable in different NAND flash memory chips. And for the future work, we would like to extend this work, the evaluation, to TLC type, more compact, and QLC storage type. And we plan to extend this work to more 3D NAND flash sample. Thank you for listening.